Hello everyone. Did you know that supermassive black holes would float in water? You may be wondering, what are you talking about? Black holes' gravity is so strong, even the light cannot get out. How can that black hole float in the water? Let me explain.
Mysteries of the universe.
To see if a black hole floats in the water or not, we need to calculate the density of a black hole. If the density is higher than water, it's going to sink. If the density is lower than water, it's going to float, right? First, we need to calculate the radius of a black hole. The radius of the black hole is a distance to the event horizon. So event horizon is the boundary. Within the event horizon, nothing can get out of the black hole. Even the light cannot get out of the black hole. That's why it's called black hole. And then size of event horizon can be calculated by the Shabbat Radius, taken after the name of Karl Schwarzschild, who found this Shabbat Radius. Karl Schwarzschild was a genius. He's a German, and when he found this Shabbat Radius, he was fighting World War I in Russia. While fighting World War I in Russia, he solved Einstein equation, and he found first exact solution of the Einstein equation, which is Shabbat solution. And Shabbat radius is one of the parameters of the Shabbat solution. At that time, even Einstein hasn't found any exact solution of his equation, but Shabbat is the first one to find this exact solution. Because he was still fighting the war, he didn't have time to write a paper, so he wrote a letter to Einstein. Einstein was amazed, and then he published Shabbat solution and Shabbat radius. This guy is amazing. Anyway, I wrote down Shabbat radius here. Rs is a Shabbat radius, and we can for now forget about g, gravitational constant, and c, the speed of the light. These are constant, so we can forget about it now. And what's important about this equation is Shabbat radius is proportional to the mass of the black hole m. So as black holes get more massive, its radius becomes bigger. That makes sense, right? What's important here is radius and mass are in proportion. So the radius gets bigger in proportion to the mass. So that's the important point. Okay? So now we know how to calculate the Shabbat radius. So let's calculate for various objects what is the Shabbat radius. For the Earth, mass of the Earth is 6 times 10 to the 24 kilograms. And then Shabbat radius of the Earth is about 1 centimeter. So if you squeeze the entire Earth, including ocean and ice and lands, continents, everything into 1 centimeter, then Earth is going to become a black hole. That's what this Shabbat radius means. In case of the sun's mass is 10 to the 30 kilograms. So if you squeeze the sun into 3 kilometers, that's the Shabbat radius, the sun becomes a black hole. How about the real black hole, stellar mass black hole, about 10 times more massive than the sun? Then Shabbat radius is 30 kilometers. And then for supermassive black holes, for example, 10 billion solar masses, that's supermassive black hole. In this case, Shabbat radius is 2 astronomical units. AU is the distance between the Earth and the Sun, so twice as large as the Earth's orbit around the Sun. So that's Shabbat radius of supermassive black hole. Next, to calculate the density, we need the volume of the black hole. Black hole is sphere, so the volume is calculated by this 4/3 pi r cubic. And then now the density rho is mass divided by the volume. So you can divide the mass by the volume. And then by the way, this radius is, we just calculated Shabbat radius. So we put Shabbat radius in, and then we get this so-called Shabbat density. This is the density of black holes. And then rho equals this equation in the red. Again, the speed of the light c, and then gravitational constant g, and then pi, all these constants, so we can ignore for now. And then the point is density rho is inversely proportional to mass m squared. Okay, it's inversely proportional. So if the mass of the black hole gets bigger, then the density becomes, yes, smaller, right? And this is very rapid because it's inverse square, not just inverse, it's inverse square. So as the mass of the black hole gets bigger and bigger, the density quickly becomes smaller and smaller. The reason why this is happening is, as we saw in case of the Shabbat radius, the mass is proportional to radius, Shabbat radius, right? So the radius gets twice as large, the mass only gets twice as large. But volume is proportional to radius cubic. So if the radius becomes twice as large, the volume becomes 2 to the cubic, so 8 times larger. If the radius gets 3 times larger, then the volume is 27 times larger. Volume gets rapidly larger and larger and larger, while mass only proportionally gets larger. That's why density becomes lower and lower and lower, because the volume gets larger so rapidly. Okay, so now let's use this equation and then calculate the density of various black holes. Let's start with the Earth. So I said if we squeeze the Earth into 1 centimeter, it's going to become a black hole. And what's the density of this Earth black hole? It's 10 to the 30 kilograms per cubic meter. That's enormously huge density. If you compare to the density of the gold is 20,000 kilogram per cubic meter. So 10 to the 30 kilogram is how many orders? 26 orders larger than the gold density. This is unimaginably large density. Now how about the sun? I said if you squeeze the sun into 3 kilometers, which is Shabbat radius, then sun becomes a black hole. Then the black hole's density is 10 to the 19 kilogram, still 15 orders larger than the density of the gold. So this is very, very high density. However, when we look at the supermassive black holes, for example, supermassive black holes in Andromeda galaxy, which is the next galaxy to our Milky Way galaxy, the Andromeda galaxy's mass is 10 to the 38 kilograms. That we know. Then if we put this number into Subactive density, then we get 640 kilogram per cubic meter. Do you know how much water weighs in cubic meter? 1 meter, 1 meter, 1 meter, cubic meter. It's 1,000 kilograms or 1 ton, right? So density of supermassive black hole in Andromeda galaxy is less than water. Less than water's density. What happens if we put something into the water and then that thing's density is less than water's density? Yes, that thing's gonna float, right? So this is what I meant at the beginning, that supermassive black holes float in the water because their density are lower than that of water. Let's look at the TON 618. This is the largest supermassive black hole we know today. Its mass is 10 billion times more massive than the sun. And if you calculate the Subactive density of this black hole, it's 0.0045 kilogram per cubic meter. Do you know the density of air? About 1 kilogram. So this TON 618 supermassive black hole, its density is less than that of air. So if you throw this supermassive black hole into the air, it's gonna float like the air balloon. So the situation is like this. So the supermassive black hole in Andromeda galaxy is like a giant water balloon, but its size is extending to the orbit of the Jupiter. It's huge, but density is just like water. Supermassive black holes of TON 106 is like huge air balloon, but its size is about the size of the solar system, but its density is less than the air's density. That's surprisingly low density, isn't it? This is why I said at the beginning supermassive black holes would float in water. Well, of course, in reality, we cannot prepare a water pool that extends to the Jupiter's orbit. So in reality, we cannot prepare such a large amount of water. But if we could, they would float in water. There's one more interesting thing. So now we know how to calculate the density of a black hole. What if our whole universe was a black hole? What is the density of whole universe if it's a black hole? Let's try. So our whole observable universe, we know that mass is about 10 to the 52 kilograms. This includes dark matter, hydrogen gas, Earth and solar system, all the stars, everything. Then 10 to the 52 kilograms. And then using this mass, assuming it's a black hole, we can calculate the Subactive density, which is 9.5 times 10 to the minus 27 kilograms per cubic meter. This is amazingly low density. Because the mass of the universe is so large, its density is even smaller than those of supermassive black holes. And very interestingly, this 10 to the minus 27 kilogram per cubic meter, it's about the same as the density of the universe we observe today. So if we observe in average, universe contains about 5 hydrogen atoms per cubic meter. And this is similar value to the Subactive density of the universe. What does this mean? This means theoretically, whole universe could be a huge black hole, right? Density matches. This may be a coincidence, or maybe our whole universe is a giant black hole. Maybe we live in a black hole without knowing it. It's interesting, isn't it? Well, this may be coincidence, but actually there are researchers thinking about such a cosmological model. These models are called black hole cosmology or Subactive cosmology, and they're seriously considering this possibility. But this may be coincidence. Universe is interesting, isn't it? Okay, if you like the video, please like it and then subscribe to my channel. Comments and questions are always welcome down below. Thank you for watching. See you next time. Bye bye.